let's send this off and then we'll see it run. So look at that. Look at how much faster that is. That is significantly faster. That's like, this is what I can tolerate. So yeah, this is the full DeepSeek model, and well, not full, quantized to 4-bit, but at the same time, I'm only using 11.8 gigs of VRAM. Hello. So today, let's do something fun again. Let's actually get DeepSeek-V3-0324, which is the March 24th checkpoint of DeepSeek-V3 running on our system here. I have about 512 gigabytes of RAM available, and we're going to try and get this iteration of DeepSeek, which is insanely good for a local language model or a local large language model, working with llama.cpp. So I have like an opinion on how a lot of YouTube videos approach running DeepSeek. I think a lot of people tend to use Ollama and try to fit in the entire model with like either offloading to the GPU or just using complete CPU inferencing, but it ends up being very slow, like maybe anywhere from 1 to at most like 4 or 5 tokens per second, and it's just unbearable to the point where it's really like not practical for use in your day-to-day. Another thing is that even when being loaded into llama.cpp, for example, which is what we're going to be doing, there is just actually so much more room for improvement in terms of performance that we can do. And that room for performance is what I want to show in either this video or the next video, that we can get on specific systems if you have like enough memory, for example, DeepSeek V3 or even R1 running at a much faster rate. So I'm going to get DeepSeek V3 first working on llama.cpp, and then after we get a sense of how it actually performs in llama.cpp, we're going to take it to the next level and use something called ktransformers to improve the performance of the model, and hopefully you'll get something out of it. But basically right now I'm copying a bunch of I'm copying the original model from Hugging Face that I stored in my file server to an SSD on this computer locally. It's about like 1.3 terabytes for the full model. It's like 671 billion parameters. So if you multiply that by like 2 bytes per parameter for 16 bits, you get about 1.3 terabytes. So what we're going to do is we're going to turn that into a GGUF so that llama.cpp can read that in, and then we're going to quantize that GGUF to about Q4, using Q4, so about 4 bits. That should take the size of the model down from like 1.3 terabytes to a quarter of that, which would be like a little over 300, maybe 350 gigabytes. I don't know, something like that. But basically, it should be able to fit into memory with some room for context window, so that we can do some sort of experiments with it. But yeah, so I'm going to just let this finish copying, and then we'll check back later and get started with our conversion process of these safe tensors to GGUF, our quantization process, and then finally testing it out with llama.cpp. And yeah, so just heads up, the spec of the system, I guess for sure it's 512 gigs of RAM. It's like DDR5 5600, but the CPU is a Xeon W5-3535X. So that's like a Sapphire Rapids CPU. So it's an Intel. It has 20 cores and 40 threads. So it's a very powerful system, at least for the time that I got it for work. Since then I've kind of switched my work machine to something a little lighter weight and decided to get serious with all my AI work on this bigger machine. But yeah, it's a 20 core 40 thread machine, and it has 512 gigs of RAM. It's not like 2025 modern, it's more like 2023 2024 modern, so it's still a realistic platform to be on. And yeah, we'll wait for everything to copy, and then I'll come back later and do stuff with it. Okay, so it looks like we're done copying everything. Let's see how big all of this was. Oh, actually not too bad. It was 688 gigabytes. I don't know why I thought it was much bigger. That's interesting. Huh. Yeah, well, maybe I was mistaking it for DeepSeek R1. Maybe that's the bigger one. Not too sure why. So anyway, it looks like we have everything in here. So maybe these are compressed. Doesn't make sense to me. Okay, so we have 600 and whatever billion parameters. Let me see. DeepSeek V3-0324 parameters. How many parameters do we have? How do we look at this? Too many things. Oh, right here, 685. Oh, but it's BF16, so I'm guessing the optimization makes it close to 1 byte per parameter, I guess. We'll learn about that down the line. Right now, I'm just interested in getting this into a GGUF file so that we can run it in llama.cpp. So, where is our stuff? Well, we mounted this drive in media average dev, and then we're just gonna look to DeepSeek. So if we did cd media average dev data DeepSeek, oh, it's already there. Okay, we have everything in here that we need. So we can just do pwd to get this entire path. We're going to need that later. Now what we want to do is we want to run our convert HF to gguf.py script. So in order to do that, we should probably go to our llama.cpp repo, and then we're going to source our virtual environment. Oh, what's going on here? Yeah. So now we're in our virtual environment, and we have this convert HF to gguf.py file. So if we could just run that through Python convert HF to gguf, but we want this one, this home here, or sorry, this output file here to be different. We want this to be media average dev data, and then we'll say DeepSeek-V3-0324.guf, and then we want that source path to be, I think it was just this one right here, media average dev data DeepSeek-V3-0324. So we did that. It should start to convert. Oh, what's going on? This gguf file is for little endian only. Huh. That's interesting. Why would that be? Okay. GitHub repo first. But yeah, I think their GitHub repo actually shows how to do this to convert it correctly. It's basically this script here, fp8 cast bf16. So I think the reason why, if we check back to our model, I forget what, we saw that there was like 685 gigs, and I was kind of tripping out on like, why is it so small? Because I thought fp16 was 2 bytes per parameter, but it's because this thing's a fp8 weight model. So we need to cast this to bf16 apparently for llama.cpp to recognize it. And so if I run this script in the repo, I should be able to convert this model to bf16, and then I can convert it to gguf. I could try that. So I think what I need to do is I need to clone this thing, this repo, and then I'm going to run this script here after installing virtual environment. Yeah, let's do it. Let's do it. So real world developer stuff here. So I'm going to deactivate this thing, and then I'm going to go up one, git clone. Yeah, the DeepSeek repo. And then if I go into the DeepSeek repo, I can start a new virtual environment in here. This is the first time I'm doing this. I don't remember how I think I used some pre-canned gguf, probably from Unsloth, and yeah. But this we're doing it from scratch. So so we're gonna do pip install requirements. Where is that at? I think it's an inference, and then there's a requirements.txt there. So we'll install all of that, and of course it has to download all the PyTorch, all the CUDA stuff again, because it's a different environment. We'll check back again. Actually, while it's downloading, let's just look at what the script is doing. So this script from the DeepSeek repo looks like it is assuming safe tensors. Okay, so it looks like it's assuming safe tensors. It converts fp8 weights to bf16 and saves the converted weights. So I'm guessing I need a lot more disk space here, but looks like it takes in the path for all the weights and the model index file, which we already have copied, and then we just need to provide an output bf16 path. So I think I'm going to be running out of SSD space soon. I only have like a 4 terabyte drive on my on the SSD that has the original model, but it's okay. So it's just 2 args necessary, and it looks fairly straightforward. Yeah, so I just hope this script works for us. Oh, it's fairly short too, so it's okay. What is it doing? I guess it's using a bunch of libraries. TQDM. Don't really know what that is. We'll figure it out. So torch set default D type. So the data type is going to be in BF16. So block float 16. And that's like I would like to say it's like a dynamic 16-bit. So it's still like lighter than a regular 16-bit data type. Yeah. Okay. So 2 args are necessary here. I wonder if there's help text. Let's see. CD inference. Let's do Python fp whatever dash help. Okay, great. So it wants input fp8 hf path, output bf16 hf path. Will this work? Let's see. Python input fp8 hf path. Path media average dev data DeepSeek. Okay, so that's the input path. I want it to go into the same place, except it's, oh, I need a switch here. Output bf16 hf path DeepSeek DeepSeek-V3-0324 BF16. Let's just tack on that BF16 there. Hit enter. Just hope. No, it doesn't work. Why? Permission denied. Oh. Okay, that's fine. I could just make dir. Make dir. Oh, no. The reason why is because I'm missing data. Yeah, that's the reason why. Okay, let's try that again. There we go. So it's gonna process all 163 safe tensors file, and it already failed on us. Why? FP8E4NV data type is not supported on CUDA Arch 89. What does that mean? Really? No, I do have a relatively recent graphics card, I think. A1. Oh, I do have an Ampere. I have A4000. Oh, what am I gonna do? Oh, I'm screwed. Let's see. What should I do here? What should I do here? Can we do this one? No, this is not even the same script. Let's see. Let's do DeepSeek. I'm getting errors. A100 is not supported. This model requires FP8 tensor cores. I have an A4000, which is also the same, I think, generation as the A100s. So what do I do? Okay. So I guess DeepSeek, we could download this one. I can't. So I physically, my card physically can't convert this because it's too old. Apparently, it's too old of a card. What do I have? An RTX A4000. What is that? Doesn't have FP8 tensor cores. That's ridiculous. Doesn't tell us here, huh? Okay. Doesn't tell us here. Second generation RT cores, that sounded fancy. Third generation tensor cores, that sounded fancy too. Specifications. Oh, datasheet right here. Okay, convince me. Let's see. Okay, what am I looking at? That's it? Okay, well, I'll take it as it is. Okay, so what I need to do then to make up for this is to get this version. This is already a converted BF16 apparently. So this one should already be BF16. Can I just search for that? I'm not even sure. This is like old DeepSeek. So DeepSeek BF16. Let's see if we can find another version. So we have this one. We have Unsloth. I kind of want to just use the Unsloth one. So this is the old one. When was this one? I want the 0324 one. This one was checked in when? 3 months ago. No. I don't want that one. DeepSeek V3-0324 V3-0324 BF16. Want someone who looks credible. Model cloud. Let's sort by most downloads. Guess model cloud. Oh, Unsloth has one. Updated about 21 hours ago. Oh, this one's relatively new. Yeah, from Unsloth. I like Unsloth. I've actually got in touch with them once before. Okay, so how big is this going to be? It's going to be very big, I bet. Yes, 163. 8.6 times 163. 8.6 times 163. That's going to be 1.4 terabytes. So that's exactly the size I was thinking. So this is going to take up like the rest of my hard drive, but that's okay. Let's do it. And then I'll check back again. Okay, so we're going to git clone this. That's a bummer, but it's okay. So I can just rim wrap everything. Let's just do that. DeepSeek this one. Okay, all our work gone. So I rim wrap this one. I'll also rim wrap the DeepSeek V3-0324 BF16 too. See, it takes a while because it's so big. It's going, I bet. I hope. But yeah, that sucks. It sucks that we don't have a graphics card apparently that supports FP8 tensor cores or whatever that means, right? We don't have native FP8 support on each core. So we had to just do it the other way where we just grab it off from someone else. That's a shame. I should probably do tmux just in case. I have a habit of closing windows, so. Okay, so let's just download that, and it's gonna take a while. So what we can do is we can monitor everything by doing a split here with btop. Capt install btop. Btop. Okay. All right. So we're gonna watch the network activity go. So I'm downloading at 100 megabytes per second. So I'm going as fast as I can. All right, I'm going as fast as I can. So, yeah. And I have, what is it? My disks. Do I have not my big disk? I only have my little disk here. There should be another one. Let's see. Oops. How do I use this? Yeah, whatever. Okay, so just gonna let this go, and then once it starts to like calm down, I know that's done. And then hopefully again, we'll have something. So I'm gonna pause this recording again. Okay, that download took way longer than I thought. It's already the next day, but I think I finally have the thing completely downloaded. It was like 1.4 terabytes. So if I go to media, oops, it's a BF16. No, where is it? What do I have? Oh, I'm not mounted. There we go. Let's see. There we go. So yeah, I have this thing downloaded, and I just did a quick, like maybe 5 minutes of trying to convert this thing to make sure that it would be successful last night before I just went to sleep. Didn't finish it. I just decided to Control-C everything, so I'm gonna clean up, and I'll do everything with you guys this morning. So the goal is to get this thing running on llama.cpp. Okay, so we have our folder DeepSeek V3-0324 BF16. Inside we have a bunch of files, right? We have the safe tensors files that we need to convert to GGUF. So we need to go back to our repo for llama.cpp. And we're going to activate our virtual environment and run the convert HF to GGUF script on this directory up here, right? So we're just going to do, I think, Python convert HF to gguf.py out file, going to be the gguf on the same directory. And then finally, we're going to point it to this directory here. So it's already been written because we tried this once before. So if I do that, it's going to try to process what? Oh, is it BF16? BF16, yeah, there we go. So it's going to try and process this thing to gguf. And I do think that it does take a while. There's 1.34 terabytes to process. And looking at my SSD here, I think I've used 3.1 terabytes already. So I don't know if it's gonna fit. So I am going to maybe empty trash here. Maybe this needs to be emptied because I have stuff in there. Nope, I'm still screwed. So we have to figure something out before we run out of space. I can move this stuff in here. It has all a bunch of like training related things that I've done in the past. But I have backed that up. So I'm just gonna remove it. So let's free up some space. Let's get rid of stuff because we're like really tight on space now. So I have 788.2 gigabytes free. The model I expect is going to be 1.4 terabytes again, because it is still it's not like compressed. It's just taking all those safe tensors and combining them together. So I'm hosed. I don't know what to do. I don't have enough space for this, so I had to figure out something. Should have thought about this earlier. Why is it taking so much space? First of all, it's 1.4 terabytes. I have a 4 terabyte disk. What is being used? I don't get it. Is it because this is already I should have like half, right? How do I? Okay. This one here is 1.4 terabytes. And my disk has 806 gigabytes free. What is going on? What do I have? Maybe I have some hidden file. Alright, going to a new terminal here. I wonder if I can just do lsla media rdev data and see what we have. Is it because we have trash here? Is that the reason why? Let's see. If I did rimraf.trash, oops, media average dev data dot trash. Actually, let's see how much is in here. The cd to that. We still have time. There's a lot. There's still subdirectories. I forgot what was the command to recursively find stuff, but I'm guessing there's stuff here. No, there's not. Where's all this stuff coming from? I don't know. But let's rmrf.trash and see what happens. Do I free up anything in this SSD? Oh, I did. Some stuff. I wonder if there's also stuff in lost and found. Oh, permission denied. cd lost and found? Is that a thing? No. Okay, well, I think there could be wiggle room now. So if I look at this, I have already 121 gigabytes, and here it is 871 gigs free. Nope, that still does not add up. I'm still wondering where the heck is my space being, like, what's taking up space? It's making me nervous. Is there stuff in here? No. Maybe it's like buffer. I don't know. We'll see what happens. We'll see what happens. Perhaps it's already buffered all this stuff here. So I wonder though if this DeepSeek Git repo has a bunch of hidden files that I'm not aware of that I could just get rid of, like this Git folder, right? So maybe if I can delete these checkpoints, it could help free something. So rm.git, rmrf, oops. That seems pretty big. Okay, that looks like it did quite a number. Oh, look. Okay, that was what it was mostly. I don't know if I messed anything up, but it looks like it's still going okay. So yeah, it came from the .git folder, which I didn't really need. I think it just goes through the safe tensors and all the files in there. So we're good. We have some room. Yeah, I'll just leave this going, and then we'll check back. Okay, so that took a while, but it's done now. I still have about 1 terabyte free, so I just barely have enough to quantize this model. And so now that I have the GGUF, I could technically run it in llama.cpp, but that's only if I have this much RAM here, which I obviously don't. I have about 500, let's just say 500 gigs of RAM. So I need to get this model down to a size that will fit in memory. Okay, so let's do that. So that next step is to actually execute another binary that we had built in like our first video. That was in bin llama.cpp, and this program is called, where is it? Llama quantize. So this allows us to take a model, a GGUF that's encoded in one data type. Like in this case, it's bfloat 16, and reduce it down to where each parameter is a lower data type. So we call that quantization. So in this case, I want to quantize down to 4 bits per parameter. And so if each parameter right now is 16 bits, just say for example, that's like 2 bytes per parameter, right? And we have like about 680 or so billion parameters. That equals to about 1.3 whatever terabytes that we see. So if we reduce that down to 4 bits, that's basically going from 16 bits down to 4 bits, which means that we've basically cut our model down to about half a byte per parameter. So that really reduces our model down to about a quarter of the size. So then we should expect then that we have a little over like 350 gigabytes or so. So yeah, that's what llama quantize does, so that we can just see how that works with the help --help argument. So if we execute llama quantize with --help again, we'll see that we have these many options here to quantize our model to. Today we're going to be using Q4KM, which is usually a quantization that yields very little quality loss, because as you reduce the model parameter size, you start to make your model more likely to hallucinate. So you make it dumber, right? But it's found that Q4KM is like a sweet spot where you can reduce the model down but not lose too much of its intelligence in this case. And these numbers here are using, I think, Llama 3 as an example, where let's say Llama 3 starts off as 14 gigs, and if you were to quantize it down to Q4KM, you'd get the model down to about 4.5 gigabytes and some change. So that's what we're going to do. How we're going to use this is Llama quantize, and then we're going to pass in, I believe, the model, the raw model itself, and then the file name of the quantized model, and then the type, the quantization type, which is going to be one of these here, Q4KM, for example. And then finally, the number of CPU threads you want for it. And I'm just going to use all my CPU threads for this, so I'll use nproc. So the command is going to be like this: llama quantize, media, average dev, data, DeepSeek V3-0324.gguf. And then we want an output, which is going to be the same SSD, but this time I'm going to rename it to DeepSeek V3-0324 Q4KM.gguf, and then the quantization, which is Q4KM, and the number of threads is just going to be nproc. So this one should happen fairly quickly. There's about 1,025 steps to do, but if I'm using all my CPU threads, you can see that there's lots of CPU activity going on now. I have a feeling I could have gotten away with just using 20 threads here, since I'm only at about 40% usage on each CPU thread. But yeah, it should happen pretty fast. I'll just cut and check back later. Okay, so it finally finished. It took 6,442 seconds to quantize this model down to Q4 KM. So 6,442 divided by 60. That is about, oh, not now. That's about 107 minutes. And so that's just under 2 hours just to do that. So now what? If we go back to our data drive and see how big this thing is now, we see, we could just do it here too. We see that we have about 404 gigabyte model, right? So our model is 404 gigabytes, and what we have left in our disk is basically 621 gigabytes. So the lesson here is that models take up a lot of space, especially like the big ones. Okay, so it's finally time. It's finally time to run this model, right? Let's use llama.cpp to actually start this up. So there are recommended settings to do this. So we can say DeepSeek V3-0324 recommended settings. Not Silly Tavern AI. Let's see. Maybe Unsloth. Yeah, it's Unsloth that will give us this tutorial. So Unsloth recommends a temperature of 0.3 and a min P of 0.00. I don't think this is actually all too important, but for KV cache quantization, use 8-bit, not 4-bit. So what does all that look like in terms of llama CPP's commands? It looks something like this. Okay, so in this case, let's just zoom that in. All we need to do is start up the server he's using, or they're using the CLI, but we're going to use server. We're going to specify the model, and then the cache type K, that's going to be Q80. So that's the what do you call this? The KV cache quantization. Okay. And then we're going to use, I guess, as many CPU threads as possible. Let's use all our threads. And then temperature is going to be 0.3, our min P is going to be 0. And then let's just start out with a context size of 4K, meaning that we'll have 4,000 tokens for the model to remember when we converse with it. Okay, so just to even go back to even llama CPP. So llama CPP what is it? Examples, llama server. Okay, so there should be documentation here on all the arguments we can use, the parameters. So we'll just build it up from scratch. So threads used during generation, that's gonna be nproc. Okay. Process priority, we're gonna try and do 3 real time. And then context size, we're gonna go for 4K for now. And then that's about it. And the rest is just adding the model in, and then min p and temperature. And then temperature is going to be temp right there. Okay. I think min p is that underscore? He uses underscore. I think it's probably the same. Okay. Whatever. Let's go back to bin llama.cpp bin, and let's run llama server. So we can do llama server. Host is going to be 0.0.0.0.0 port. Let's specify port 9000 this time. Our model is going to be at media, average dev, data, DeepSeek, what is it? DeepSeek-V3-0324 q4km.guf, GGUF basically. Temp is going to be 3.3, and then min p is going to be 0.0, so 0.00, and then priority is going to be real time. And then let's specify, instead of all our threads, let's specify, so I have 40 threads. Let's do 38. So -t will be 38. And then is it context size is CTX, is it? Let's see here. Context size. CTX. Yeah, CTX size. So -c. Let's do -c to be -c 4096, and then finally we have the KV cache. So let's look for KV cache. Cache. Come on. Quantization. Oh, cache type K. Is it? Yes, KV cache data type for K. So that could be Q8_0. Okay. I don't know why this was. Where is it? Cache type K. Yeah, cache type K. Yeah, there we go. Same thing. So cache type K, or we could do CTK. Let's just do CTK. Okay. Actually, cache type K. Let's just do that. Q80. So that's our command. Let's see what happens. Let's try to run it. And as we are running it, I think it's worth seeing basically through some monitoring HTOP to see how much, or BTOP to see how much RAM and CPU we're using. I think HTOP will give us a better view. So let's fire up HTOP, and then let's start this thing here. So that's going to, oh, sorry. This is probably going to try and run it on my GPU too, which I don't have enough memory. So there's another switch called NGL, which will tell you to offload how many layers of the model to the GPU. I want none. Okay, so that's going to be the real command. So right now I'm using 3.3 gigabytes worth of memory, but you're going to start to at least see somewhere it's going to get higher and higher. I think it's this one. Yeah, this one right here. Yeah, this first llama server. So right now it's allocated 76 now, and then if we look at some CPU activity, we see that we're working to load stuff into memory right now. So basically the entire model. So yeah, that's gonna take some time. Again, we'll check back maybe 5 minutes, see what happens. Okay, so I think that finished loading. So how I know that is usually when llama CPP fires off this like warm up message. Yeah, don't know why my memory usage still says like it's only about this much used, but okay. I would have assumed it would have loaded everything, but I think there's another option that maybe I'm missing somewhere that doesn't say that. So anyway, let's just navigate and see what happens. So here's our web interface for this specific server. I do want to turn on tokens per second. Okay, and we're going to type a message. So let's say let's ask it a question. So, can you tell me something? Oh, I know. How would I be able to create a new Git branch from the command line? Okay, so it's going to start processing. So it's not bad. It's about seven tokens per second actually for the DeepSeek here. So, and this is like the state of the art. This is like one of the best local models that you can run, right? As you can see here, maybe we have a lot of CPU activity. Oh yeah, we are pushing. Look at that, 100%. If you look at it from GUI, right? GUI here, yeah, we're really cranking right here. We only have basically 2 threads here that are inactive because we specified our model be running on 38 of them. But yeah, it's not too bad, right? Like it's not like brutally slow, but we're not even using any GPU for this. So if I look at NVTop, for example, basically nothing is loaded onto GPU memory except for I think the KV cache here, but the GPU isn't really like I guess what we call like cranked up. We're just using purely the CPU in this case here. So yeah, so that's, I mean, see what do we have here? So create a new Git branch from the command line, straightforward process. So check out the current branch, or check your current branch. Okay, so Git branch to see what branch we're currently working on. We could create a new branch, and then we could check out that branch to switch. We can combine branch and creation and check out in one command with this. Then we can do git branch again to verify what branch we're working on, and then we push to equivalent remote. Okay, and then that's about it. It gives us a workflow and everything. So that averaged about 4.2 tokens per second, so it's not too bad. Okay, prompt generation, meaning like how it processed our prompt, was almost about 13 tokens per second. It's not too bad. Let's actually keep this as like our test prompt, right? Because this is actually like a real question we would ask an LLM. I think it's fair. It's a fair question. So text editor. Okay, so let's just keep that there. Okay, now my question for myself is, can we go faster? Well, there is something I want to try out. It's called ktransformers, and it does a lot of match. So like, here's what I know. So DeepSeek is like a mixture of experts model. So it's like a collection. Basically, think of it as like multiple models in one big model. And since DeepSeek is like a 680 billion parameter model, there's like 37. There's like multiple 37 billion parameter models around, and inside it. So whenever you let's say ask a question, what ends up happening is that one of those experts, those mixture of experts, right? The expert with those 37 billion parameters are going to be activated, right? So it's going to be active, and really only 37 billion of those parameters are doing the inference for you. The rest of the parameters are just sitting around in memory. what ktransformers does is that it optimizes this flow a little bit, allowing you to gain a lot of performance by really only focusing on the active parameters as it's doing that inference. I think it does require GPU, so I think it only supports Ampere and above. So basically anything that's like a NVIDIA A whatever or 3000 series and newer, it'll support that. And they've gotten it to run DeepSeek in just 24 gigs of video memory. I have 16, so I don't know if this is going to work, but we're going to try. But basically, we're going to get significant speed up with DeepSeek, and I just want to show how much faster we're going to go with ktransformers to make DeepSeek go much, much faster on a local computer without having a very expensive GPU. But again, I do have a lot of RAM, and that RAM is also not cheap, but it is more accessible and cheaper than getting a high-end GPU just to run DeepSeek. So let's move on to that. Okay, so I think we can just follow this tutorial here, maybe. Let's see here. There's a link here, how to install. Oh, right here, this installation guide. So we could probably try to follow this. So we do have CUDA 12 and above. We put a lot of effort into making sure that works. So we don't need this. Let's see. Okay, we do need to get dependencies. So we'll just do apt update and then install build essential cmake ninja build and patch elf. I'm not sure. I'm running Ubuntu 22, so not sure if this is too old of an OS, but we'll try. Okay, so I'm going to copy that and I'm going to install dependencies. Oh, before I do that, I should just probably quit this instance here. I think it takes a while for it to clean up. Let's see. Yeah. Okay. Okay, so let's install that stuff here, and then see if we have any of these things. Okay. So after we get those dependencies, we want to use Conda. So it's kind of like virtual environment, but I guess more popular for whatever reason. I'm going to stick to the script. I'm going to try my best to color within the lines and use the Conda script. So I'm going to use mini Conda instead of anaconda because that sounds more lighter weight, I guess. So wait, why is it trying to download? Oh, it's a script. Let me just mini Conda 3. Just making sure I'm downloading from the right place, right? So let's reject all. So quick command line install. So let's go back here. Do you want to continue? Yes. Okay. Installing mini Conda page. So it installed all this Ubuntu stuff just fine, by the way. Okay, so we're gonna look at Linux, and this looks about right. So we're gonna make dir p miniconda 3, so it's gonna be our home directory miniconda 3. We're gonna wget our Linux script, shell script to install miniconda, and after that we're going to just execute that script, or we're gonna save it as a script, and then we're gonna execute that script with bash, and then we're gonna remove that script to clean up. Okay, and then after that we just source activate the environment. Okay, seems easy enough. Installing the base environment. Sure. Okay, so now to activate our miniconda environment, we can just do source miniconda 3 bin activate. Okay, and that should get us running with our miniconda environment. I still have my virtual environment on. I don't know if that's going to affect anything. You know what? Let's deactivate our virtual environment so that now we're cleaner. Okay. Next step is to create a conda environment called ktransformers using Python 3.11. So not sure if I have Python 3.11. Let's see. I think I'm using Python 3.12. So I think it'll magically create it for us. So let's see. So conda create. Okay, so it is downloading the Python for us. So let's just leave it. Let's just leave it to do that. Okay, great. And then we can just do conda activate ktransformers. That'll activate the ktransformers. Yeah, that will activate the ktransformers conda environment. And then we'll do conda install, conda forge, and then this C++ library here. So far so smooth. And then after we're done installing that, supposedly we're supposed to run this command, and what we're looking for is if we have this version here. That's how we know it'll work, I guess. So yeah, yes, let's proceed with that install. Okay, it looks good so far. And then we'll just run this thing here. Okay. Huh? No such file. Uh-oh. Let's see. Oh, it's Anaconda. No, I want Miniconda 3. Miniconda 3. Okay. So what are we verifying here? 3.4 point what? 3.4.32. So praying that I have it somewhere right there. Okay. So it looks okay. It looks okay. Okay. So yeah, we can proceed. All right. So now we had to install all these Python dependencies, torch, and then get the CUDA version for 12, I guess, and then that already provided here. See Q126 basically, and then other stuff here. So I'll just copy and paste that, and make sure when you do that you're in the ktransformers environment. Okay, so the next instruction is at the same time you should download and install the corresponding version of Flash Attention from this place here. Sure, let me do that. I'll just open another tab and do that. Okay, so it's going to be version 2.7.4 for post 1. I don't know what that post 1 means, but this is the latest version, and I'm assuming we want the latest ktransformers. So this is where it gets tricky because there's a lot of versions here, right? So what we want is it's likely that we're installing PyTorch 2.6, so we need the Torch 2.6 version. So you see this right here, it says Torch 2.3, so we need to go and look at Torch 2.6. Okay, so now we're in Torch 2.6. At the same time, we need to look at Python, right? So CP311 is what we want, but then this is Q12. But ABI should be true, so I'm looking at this one here. So I'm going to download this wheel file. So I'll download that, and then that'll just go into my downloads directory. I've already installed all this, so I'm going to install this wheel file. And installing the wheel file is pretty easy. You just do pip3 install downloads, and then flash. Where's it? Flash. How come it's not working? Average dev downloads flash. Hey, come on. Do I have to like copy everything? Here we go. Copy. Like that. And that should just install the Flash Attention. Okay, and I think that's like required for ktransformers to work. And I think we're supposed to pronounce ktransformers as quick transformers. So anyway. Okay, so if you want to use NUMA support, not only do you need to use NUMA 1, but you also need to make sure you have installed the libnuma dev. Okay, so we don't need that. We're not in NUMA configuration. I don't care about multi-concurrent. I just want the easiest thing possible. So we're going to download the source code and compile this thing. Okay. Now, there's one thing about building from source that I want everyone to know about is that you should never build from master. You should always build from a tagged release, and we'll check that out later after I've cloned this repo into my code repo directory. And if I go into ktransformers, you see how we're in main here? That's not a good thing. We want to work off of a tagged release, basically a release that they like a branch of that release, so we know it's somewhat stable. And I usually like to go with one that is more recent, right? In this case, post 1 is what we just downloaded, so it's released 2 weeks ago, so we can do that. Yeah, so let's check out post 1. So check out V0.2.4 post 1. Okay, it's gonna tell us that we're like on a detached state, but that's fine. Okay, so now we're on this this specific checkout tagged version, and then we're already here, so we need to we're already in the ktransformers directory here. So we're going to now do initialization of all sub modules in the Git repo. And then once that's done, I think it's as simple as hitting or running bash install.sh. There is a bug here. I'll give you a preview already. I'm aware of it. Balance serve doesn't seem to work for everybody, especially after like the latest version of quick transformers. Balance serve is just like a more efficient way to, I think, do multiple requests, but it's only us. So I'm just gonna set that to 0 and compile it like with the script like this. So let's see what happens. Okay, so that's done now, and then let's build. So use balance serve is going to be 0 for us, and then we're going to be bash current directory install.sh, and that may take a while. So we'll just leave it, and I'll just put a good view here. We can see there's CPU activity going on. Yeah, I'll check back later. Okay, so that was actually very pleasant. It looks like everything compiled, and the next step here is to just the execute stuff. In this case, there's actually a lot of additional things that we need to do here. First, we need to start up our server. Okay, so ktransformers, it's another inference engine, right? So it's not llama.cpp, it's different. So it's going to be a different set of argument. First of all, it's a different program, and we have to set different arguments here. So the important ones is model path, which is where ktransformers expects to find things like the config JSON and all this stuff. So it's worth keeping these files after you've converted these safe tensors to GGUF. You don't have to keep the safe tensors, but you should keep everything else in this original directory. And then you also need the path to the GGUF. And then you also can specify the amount of CPU threads you want to use for inference. And then you don't really need all of these other stuff. I think this is just for optimizations. We're just gonna run it normally. And then the port, and then I'm guessing host is another one of those arguments. Chunk size, that's gonna be the maximum number of tokens processed in a single run, okay? Max new tokens, and this is very important. This is like, it determines how many new tokens can the model generate in one go. So it could just stop all of a sudden if it runs out of tokens to generate. I tend to leave this pretty high. I really don't care if it starts hallucinating. And then max batch size, think number of requests to be processed by a single run. This is only if you have balance serve on, and we're not going to use that. Okay. What else? I don't know why they put port twice. Weird. Cache length, I think that is it has to do with like the number of tokens you use for context. I think it's also for KB cache, and backend type here will be ktransformers rather than balance serve. Okay, so the original single concurrency engine is ktransformers. So we'll use like the most basic things to try to get this running. Okay, so yes, let's do it. First, I found this somewhere. We need to set some environment variables. It's going to be export CUDA home USR local CUDA. That'll tell us where to find our CUDA. We also need to export another environment variable called torch CUDA arch. And since I'm on an older GPU, I can put 8.6. That's like Ampere class. And if you find yourself running this often, you might as well put the everything that I'm about to type into a shell script, so it's easier. But basically, the command that I'm going to be running is going to be Python ktransformers. That's a directory. Server main.py, and I'm going to start a new line in this command. I'll specify host to be 0.0.0.0, make a new line, and then I'm going to specify port to be let's go 9999, and then I'm going to specify the model path. That's going to be our media, average dev, data, and it's going to be this. That's where our like configuration files are. And start a new line, and then the model name that we want to have it be recognized as is going to be DeepSeek V3-0324 Q4KM.gguf, or we don't need to say gguf. That's for the next one. gguf path, we'll need that. So that's going to be media, average dev, data, DeepSeek Q4KM gguf. Next line. Chunk size is going to be, just leave it as default 256. We can play around. Cache length. I'm going to be pretty small in the beginning. I'll just do the 4096. And then CPU infer, CPU infer. I'll specify 38 threads, and then max new tokens. I think I'll specify 1024 for now. Again, something we could play with. Temperature is something that's necessary. That's somewhere in the documentation. And then backend type will be ktransformers. And we can just execute this, and then we'll be able to use the web API. So, okay, so this is what I was scared of. This is a missing dependency. I have never figured it out, but I know a workaround for this. So it's going to require us to modify some code. So basically, I have notes next to me here so that I know what to do. We're going to have to edit some of the Python scripts here. But before I do that, I'm going to make a shell script with all this stuff in here. So maybe I can throw this into one side, and then there's another window here that I could use. We'll just put this on our home directory. We'll see vim starts DeepSeek v3.sh, and then we could say shebang bin bash. We'll say export CUDA home user local CUDA. export, what else do we have? Torch CUDA arch. Torch CUDA arch is going to be 8.6. And I think we can just copy and paste everything here. Okay. Right there into this script. So should be easy. We'll save that. And then we'll chmod the script plus X with start DeepSeek. So we're going to add execution to this shell script. So if we do LSLA, this will be green here, meaning that it is executable. Okay, done. Now, let's edit some Python files. So the first file we need is in this location here. So vim mini Honda 3. We're going to go into the environment, the ktransformers environment. Inside is a bunch of libraries. What we're interested in here is going to be in the ktransformers pip package or Python package, and it's gonna go in models. Was it? Is it models? No, it's settings. Side packages ktransformers server balance serve settings.py. Since we're not using balance serve here, it's safe to just modify this code. So what we want to do is we're going to do try import sketch extension, I'm assuming, and that's going to basically throw an error for us. It's going to be an import error, and what we need to do now is just set that module to none. Okay. So that's one piece. Another piece of code that we need to make changes to is the custom cache code. So we go back to ktransformers. There's a models folder. There's going to be a custom cache.py, and I think it's this one here. It's the same thing. We just need to do try and then accept. So accept import error, but we're going to give a dummy implementation. So it's going to be class dummy module class inference context pass, and then I think it's just assigning this to be an instance of our dummy module. Okay. Now we need to also get rid of any type hints with skegx because it doesn't exist. It doesn't have properties. So that's going to be in the DeepSeek-V3 cache, and I think the place that it's going to need modification will be this load here. We just need to get rid of this type hint. So this type hint can just all go away. And that's it, I believe. Yes, that's it. So save one more time. Okay, so let's execute our script. Or we can just do this again. Actually, let's test our script. So we can do bash. Was it start DeepSeek-V3.sh, and then hopefully it works. Okay. It should try to use some of our GPU too to offload things. Oh. Key output.wait not found in safe tensor files. Why is that? Interesting. Safe tensors files. So let's just look it up. Okay, so someone has had the issue too. Is it because our GGUF path is wrong? Maybe. Let's see. Is it? I don't know. How do I translate this? Let's see. To English. Huh? Oh, you know what we can do? Let's see. Let's start up Open Web UI and then source.venv then activate Open Web UIs, or we can start our model, right? So what was that again? Start Quen. Okay. Okay, we'll start Quen, and I think we don't need Open Web UI. We can just tell it. We can just go here. Okay, so whoa. Why are we in here? Okay, let's do this. I don't know Chinese, so we can go here. We can copy this, and we can say, can you translate this to English for me? And translate to English from Chinese for me. So let's see. Separate the GGUF files and save tensor files and provide the paths. When specifying the path, use GGUF path to indicate the folder and do not specify the GGUF file. Oh, okay. So that was a wrong script. Cool. Well, thank you, Quen7b. Let's hope that works. So let's actually put this GGUF into a folder. So we can say GGUF. So DeepSeek-V3-0324, Q4 KM, and then let's just make that into a directory. Oops. Okay, so we're gonna turn this into a directory by just simply doing this. New folder, DeepSeek V3-0324, Q4 KM, and then we'll just chuck that in there. And now let's see what happens. I should probably kill this one too. I might need GPU memory, who knows. Oh, it looks like it's working. Great. All right, cool. Thank you, local model. You helped me, I think, hopefully. Okay, so let's see GPU activity. Let's see what happens. Let's see if we can actually fit stuff in. Will it work? Will it work? Let's check back. So it's loading all the stuff into memory right now. Well, looks like it magically worked. With only 11.5 gigs of VRAM being consumed. Maybe it's from other stuff too, but we have an endpoint here that we can hit. I think really it's just regular REST API. I think if we did V1 models, yeah, we'll just have like information about our models. In order to do any inference, we need to use Open Web UI for this. So let's just start up Open Web UI. So we do Open Web UI serve with our host. I wonder if I have enough memory. Yeah, it seems, I don't know. Yeah, I think we're all running in RAM here. So let's see, top. Yeah, so 380 gigs in resident. Okay, so let's go to Open Web UI. So we need to hook up Open Web UI with this server here. So that is just basically an OpenAI compatible connection. So if we were to go to this admin panel here, there's a connections tab. We can just add an OpenAI API. Same thing with llama.cpp, but in this case now we're on port 9000. What was it? Port 9999. So port 9999/v1. Okay, API key none. Okay, so now let's see. We go to new chat here. We find that we have our model listed. All right, let's give it a prompt. Let's see how much faster that is. I don't know if there's a tokens per second here, but we can watch. So I can watch on this side maybe, and let's see what it does. So let's do it. This doesn't look right. Okay, so what's going on here? too many levels of symbolic links. What's going on? Let's see, flash infer. Okay, the latest MLA kernel flash still has a few minor issues. If you're using flash infer, please install it from the main source code. Oh, that's joy. So we have to install flash infer. How do we do that? Here, pip install. Okay, sure, let's do it. I don't know what to expect. Okay, let's do it again. It says I already have it, so I don't know what that means. For JIT version, compiling every kernel from scratch, MVCC is required. Let's do it like this. This is good. So wait. There was a thing about this. The latest MLA kernel and flash services they are continuously fixing the main branch. If you're using flash, please install it from the main source code. What does that mean? Does that mean I have to build it? Oh no. That's gonna be a hassle. Ugh. What I'm going to do is I'm going to just clone the repo and install from source. So let's see what happens. Okay, so let's just clone all this. We're gonna build from source, and I think the instructions from ktransformers said to just start from the main branch. So yeah. To precompile essential kernel, set the environment variable flash infer enable AOT before running the installation command. My goodness, they should put that in front before I do anything. I'm glad I actually read all that. Okay, so how do I uninstall flash infer? Pip uninstall. How do I do pip uninstall? Is it just pip uninstall? Yeah, pip uninstall. So I can do something like pip uninstall flash infer Python first, just to get rid of that old stuff. I'm gonna cd flash infer, and I'm gonna set AOT equals 1. So do that. Well, let's see what happens. Oh man, I hope this works. I should probably write up a guide once all this is done. I don't even know if I can reproduce any of this, but I guess I can watch this video, right? That'll help me. So yeah, I'll pause. Okay, it says too many levels of symbolic links. Oh, I think I might know why. Okay, it might be my environment variable. Okay, let's do this. ls usr local CUDA. Too many levels of symbolics. That might be the reason why. So that might be the reason why everything. Okay, so let me think. I should set CUDA home to be something else. I'll set it to CUDA 12. How's that? This CUDA here is broken. I should fix that. Maybe I can fix it now. lsla usr local. So this CUDA goes to where? CUDA 12.8. USR. Oh my goodness. So this is like a loop. Okay, how do I fix symbolic links? Remove symbolic link. I think I just can do. Okay, fine. So I can do rm USR local CUDA, and I think, oops. So I think this was the problem. I didn't need to do all that stuff. Okay, now how do I relink? So I want to go to CUDA 12.8. So add symbolic link Linux. Okay, so LNS, this will be a symbolic link. Okay, so I can do LNS existing source file, optional symbolic link. So give me an example here. So I can use LN to create a new symbolic link called that. Okay, so this is the link you want to create. This is the source. Okay, so I could do USR local CUDA 12.8, and then I'm gonna link that with USR local CUDA, and I'm gonna sudo. Okay, so after so much fiddling around, I can confirm that it was my environment, well, not environment variable, but it was my USR local CUDA symlink that was causing all the issues. So flash infer, everything, all that stuff that I did was totally unnecessary. All I needed to do was just fix my symlink. I fixed my symlink, and then I just redid the whole build again, and I actually tested this before resuming the recording to make sure, and it works. So I want to show you what it's like when we use quick transformers as opposed to anything else. So what we can do is we can bring back our prompt that we had, which we don't have here. What was it? I think we probably have it here too. So boom, right there. Okay, so if I passed in the same prompt, technically I should be getting faster performance. So before it was like maybe, what was it, about 4.2 tokens per second, but now running this new server here with Open Web UI, I may not get the statistics. Let's send this off, and then we'll see it run. So look at that. Look at how much faster that is. That is significantly faster. That's like, this is what I can tolerate. So yeah, this is the full DeepSeek model, and quantized to 4-bit, but at the same time, I'm only using 11.8 gigs of VRAM. So there's a lot of potential in this. I mean, sure, I need a lot of RAM, but holy moly, it is so much faster than using it through llama.cpp. I think it's pretty cool. I think more people need to kind of just show this off, you know, when they're doing CPU inferencing or like low-end GPU inferencing. Yeah. So what are the stats? Are there stats here? Let's see. I think it's here. So yep, that's it. So I know people also like to do this benchmark of like writing a story, right? So, you know, write a 500-word story, something like that. Of course, in this case, that might exceed the max token settings that we have. So let's actually push it a little. Let's see how many tokens we can actually maintain. So I have 4. What was it? Was my context window was 4K. So let's actually quadruple that and see how much memory we might end up using. And it's, again, fast. So yeah, again, I think the community needs to promote this method more instead of just using, I mean, no hate against llama.cpp, but there are ways to make DeepSeek go faster if you want to try it, you know. I think quick transformers is the way to go if you want that. Yeah. So it looks like it's true. The two things that we need to change is just basically the max new tokens in the cache lens. So I'm gonna increase this to 16384, and I'm going to increase this one to let's be brave, and also increase this by 4 times the amount. And let's see how much RAM we end up using. So, or at least VRAM. So right now we're only using like 1 gig, right? Oops, maybe I should have just did it like this, and then at the top. Woo! Okay, I briefly saw that as at 13 gigs. Will it work? We'll see. So it does take a while to load all this, so I'll pause the video again. Okay, so HTAP is slowly showing that we're climbing up in memory here. So we have it's like 153, and looks like we're like halfway there. Loading, there's like 60 layers. We're already, for sure, we're gonna hit over 11 gigabytes this time. Will it fit on my 16 gig GPU? We'll see. Be pretty cool if it did, because if I say that, and I've actually gone this far before. I've actually used it for real work, DeepSeek for real work, and I've never, like, I've gotten to about like 32,000 tokens context length, and that was like really pushing it. Like I was forcing it to be long. But normally, if I'm like just doing normal work, I never really go past like 16. Even if it's like coding stuff, it's just normally like quick code snippets. So I'll be happy if I can get to 16. I'll be like satisfied. And if it's like 16 in terms of good performance too. So okay, so now we're here again. We're in a good state. Let's create a new chat, and then let's just I don't know if this is gonna work, but let's see. Again, right? Actually, let's do the same prompt. It should go around the same speed. So might need a warm up though. Let's see. Let's do a quick warm up. Hi. I don't know if it does the same warm up as llama.cpp. So just doing it in case, and then same thing here again, and the performance should still be about the same. So there we go. It's not too bad. It's pretty fast. Look at that. This I like this. Okay, so if I look at the RAM usage, it's 380 gigs. I don't even know how to tell how much RAM I have. Oh, 75.7%. I'm using 12, almost 13 gigs of VRAM now. So I think I have a little headroom up to up it to about maybe 24K context window. But I think you guys get the gist by now. I think it's just more like experimentation and just see what's up. But yeah, this is the hype. This is what everyone wants to run. It's DeepSeek. Either the R1 or V3, doesn't matter. I think V3 has, for me, in my personal experience, has been the better model for what I need. But if you need some problem-solving reasoning model, you can also do DeepSeek R1 too, I believe, here, because it's based off of the same architecture. Super long video. Most of it is just me not being prepared, but I just wanted to show everybody something different. I guess like what you would normally see in other videos. So hopefully you can find a way to try it out. Maybe, I don't know. Hopefully, if you can find the amount of RAM. I know I'm very blessed to have that much RAM. So, but there's no way I can get that many GPUs, at least. Thanks, everybody.